And the first one here is just applying the formula. W is W minus alpha times AI minus YI, and then XI. So the W is 1 minus 1, and alpha is 1. And A, you need a dot product, so it's W dot X, which is just 1 times 1 minus 1 times 1, so it's 0. And 0 is indeed larger than or equal to 0. So the indicator will give you 1. So our A is 1, Y is 0, and our X is 1, 1. So it's 1 minus 1 minus 1, 1. So it's 0 minus 2, and the answer is 0 and minus 2. On the next one, the key point here is this is not dot product. This is the just matrix multiplication. So W is W1, W2, and transpose is W1, W2. So just do it as a matrix multiplication. The first row, first column, W1 squared. First row, second column, W1, W2. Second row, first column, W2, W1, and the last one, W2 squared. So then in the question, there's a trace. So there should be a trace here. And trace is just the sum of diagonal values. So it's W1 squared plus W2 squared. This is just the cost function. And then differentiate this twice just means differentiate once is 2W1, differentiate twice is 2. And similar for the other ones, you get 2, 0, 0, 2. And that's the answer. And the next one is asking which ones are eigenvectors. So just try all of them. Let's try the first one. 1, 0 is some number times 1, 0. So row, column, row, column. So its row column is 2 plus 0. The other one is 0 plus 0. So 2, 0 is some number times 1, 0. So this number will be 2. So our first eigenvalue is 2. You can do it for the other one. Let's try 0, 1. Then you get 0 and 2. This is just 2 times 0, 1. I mean, 0, 1. Eigenvalue again is 2. So if two eigenvectors share the same eigenvalue, then what it means is any combination of these two eigenvectors are also eigenvectors. So for example, if you add them, then it's 1, 1. That one is also an eigenvector. If you do the first one, subtract the second one, you get this. This is also an eigenvector. And also, second one, subtract first one, you get this. It's also an eigenvector. And minus the first one, minus the second one, also eigenvector. That's why there are 6. So in general, if you have different eigenvectors, then you cannot do this. But if you have the same eigenvalue for different eigenvectors, you can combine the eigenvectors to get new eigenvectors. Let's move on to the next one. And this one, the first step is just substituting this thing into this expression. So it's 0, 1 minus wx and yi. So we know the data points, so we can substitute in because we are just differentiating with respect to w, so we don't care about the other values, so it's just 1 minus w. Let's actually draw this. This is 1 minus w, suppose this is w, 1 minus w is just that, and 0 is this, the max of these two is this part and this part. And at 0, you see it's only this part. This is w equals 0. Because at the beginning it's 0. So when we take the derivative at 0, it's just minus 1. So that's why w is, so the gradient descent step is just w minus alpha times the gradient with respect to w. And this is 1. This from the diagram is minus 1. So if w is 0 is here, then you need to worry about the subderivative stuff. But here, there's only one, this is differentiable, it's a line, so the derivative is just minus 1. Also, if w is equal to 0 is here, then the derivative will be exactly 0. But in any case, here is minus 1, and the original w is 0, so it's 0 plus 1 is 1, so the answer is 1. And similarly, you can solve the other one the same way. Let's write it down quickly. So this is 0, 1 minus x now is minus 1, so it's plus w. So now it becomes the other shape, I think. I think it's something like this. And w0 is here. So the max of the two, when w is 0, this is larger, so we know we are on this side. So we know, and we also know the derivative is 1. So w, again, is w0 minus alpha times this derivative. And alpha is also 1. This is just plus 1, so that's why you get 0 minus 1 and minus 1 here. The next question is just a fancy way of saying we don't have weights, we only have bias term. So we're just trying to fit functions like this. So for example, if b is 3, then what happens is, let's have a row for y hat. If b is 3, then anything above 3 will be classified as 1 based on this. So this basically means these are 1 and these are 0. So it means everything is classified correctly, so the accuracy is 100%. So the number of mistakes is 0. That's why the cost is 0. If you look at this expression, this is just counting the number of y hat that's not equal to y. So basically counting the number of mistakes. And we want to choose a b such that the number of mistakes is minimized. So here, the first one should be obvious. The second one is slightly tricky, so we can try different values. So say b is 6. If b is 6, then it will be classifying everything as 0. And if it's above 6, then it's 1, but it doesn't matter. So how many mistakes? So there are 2 mistakes. Mistakes is not spelled this way. And if b is 0, then it will classify everything as 1. So 1, 1, 1, 1, 1. So 3 of them are incorrect. So comparing these two, of course, you can try other numbers. You can try 3. If b is 3, then it's classifying these as 1, these as 0. So there are 4 mistakes. So of course, this one is the smallest. We want to minimize the number of mistakes, so the answer is 2. So you do the last one the same way. You try different ones. I think if you put b is 5, it will work. No, b is 4, it will work. So you classify 0, 0, 0, 0, 1. Then the cost is 1. And the next one you have, this is convex. So you know that a must be larger than or equal to 0. You should draw it. If it's a is larger than 0, it looks like this. If a is smaller than 0, then it's the other way, and these ones are convex. So we know that a is larger than or equal to 0. When it's equal to 0, it's just flat, so it's also convex. And then given that, you need to figure out which one of those are convex. So the first one, I think you should draw it. It's just some number multiplied by the absolute value, and the absolute value is convex because you take 2 points, you connect the line, and the line is above the function. And I said weakly convex is because if you take 2 points here and you make a line, it's on the curve instead of above the curve, so it's also called convex. So it's basically weakly convex just says strictly convex plus those linear pieces. That's the first one. And the second one is you have this shape. Of course, if you connect 2 points, it's below the curve, so no. And the next one is like this. It's also, if you connect any 2 points, it's always above the, the curve. So the next one is a times something minus 1. So the curve looks like this. So I think it should be easy to see if you connect 2 points, they are some part of it is below the curve. So that's not right. And the last one is this one. If you connect these 2 points, they are the line is below the curve, so that one is not convex as well. So one thing is that if you restrict the domain to a non-zero domain or a positive domain, then this part is actually convex. The other part is also convex. But if you connect them, then on the real domain, whole real domain, there are lines connecting the 2 points on the curve that's below the curve. So that one is not weakly convex. Mm. Next one here is the neural network one. So you have an image. So the input layer has 9 units, and I don't know what the hidden layer is. Let's call it M. And then the output layer is 1 unit because it's binary classification. So it's fully connected. So everything is connected to everything. So there are 9 times M number of weights in the first layer between the first two layers, and there are M units, M weights between their hidden layer and output layer. So there are in total 10 M weights, and there are 90 weights. So M is 9. So there are 9 units here. With each unit, there is a bias. So there are 9 bias terms in the hidden layer plus 1 bias term in the upper layer. So there are 10 bias terms in total. So the next one, there is a bit of confusion with the notation. So these two are the ones connecting to the first unit of the first hidden layer. Let's draw it. So this is x1, this is x2, and then this is w11, this is w21. So what it means is, let's erase this. This is plus 2 and this is minus 2. And similarly, this is minus 4 plus 4. These are the activation units. And at the end, it's minus 2, minus 2. And this is the output layer. So if you can draw the network correctly, then I think doing the activation should be simple. And also it's LTU, so all of these are either 0 or 1, so you don't need to compute the logistic thing. So here, let's try the first one. If it's 1 and 1, then you put 1, 1 here, then this unit means it's 2 times 1 plus minus 2 times 1 plus the bias term, which is minus 1. You get 0 minus 1, so this is minus 1 here. Minus 1, remember, we're doing the indicator, so minus 1 gets to 0, so this is 0. And similarly, the other one is minus 4 times 1, 4 times 1, minus 2, so this is minus 2 again, it's turned to 0. And 0 times minus 2 is just 0, and the bias term is plus 1, so that's why this thing is larger than 0, so the indicator would output 1. So what it means is the output here, y hat, which is just a2, is equal to 1. You can repeat this for the other ones, so you can just do these two, and then you should be able to get that. The next question is the KNN1. So twofold cross-validation. So this is the first test set. This is the second test set. So what it means is we train on these and we test on these. So let's test the first one. This one, the closest one, using Manhattan distance, just take the difference and add them up. So this is 2 plus 3, so it's 5. The distance here is 4 plus 4, so it's 8. So basically it means this test point is closer to this training point. So you label it the same way. So you label it 0. And similarly, this one, of course, is closer to this one, so you label it 0 as well. So half of it is wrong, basically. And then you repeat the same thing using this as the training set and using this as the test set. So this one is closest to, I mean, um, this one is closest to this test point, so you label it 0. And similarly, this point is also closer to that point, so you get 0 as well. So two of them are classified incorrectly. So it's 50% correct. And fourfold cross-validation is the same idea. You just take out the first one, train on these three. The nearest neighbor is this, so you classify this as 0. And similarly, the nearest neighbor, you need to compare the distance between this point with this and this point with this. And turns out that this one is closer, so it's labeled 0 as well. And again, all of them will be labeled 0, so you get 50% correct. Um, for these two questions, you don't actually need to do anything because on the midterm it's multiple choice. So you have multiple possible answers, and what you do is just substituting all of them to here and see which one gives you the lowest number. So it actually minimizes that. And also you need to remember to check that they do satisfy this constraint. So substituting W1 is -1, W2 is minus half, and W2 is half into this, it works. So remember to check, and after you check them, just substitute them into the objective and see which one actually minimizes compared to the other choices. And you do the same thing here. The next one is an SVM question. So there are three dimensions, x3, say x1, x2. They are not actually important because they're always 0. So the 2 points are these 2 points, 0 and 2. So of course, if you want to put a plane to separate this, so the plane should be like this. So it basically should pass through that point. So and and the equation of the plane should be kind of obvious. It's just x3 is equal to 1. Because everywhere on the plane is just x3 equal to 1. And x1 and x2 can be anything, basically. So you just need to rearrange this, and this is 0x1 plus 0x2 minus 1 times x3 is plus 1 is equal to 0. So that's the equation of this plane. And then the last thing is to decide whether above the plane is 1 or below the plane is 1. The trick is you can just substitute this 0 into that expression to see what it gives you, right? So if you this is 0, 0, 0 plus 1, so basically says it's an indicator whether 1 is larger than 0, and this is always true, so it's always 1. So the label must be 1. If it's 0, this cannot be classified as 0. So this is impossible, and in this case, you just use the coefficients 0, 0, minus 1 here. The question here is the main trick is to write out this matrix F. So the matrices are indexed by starting from minus k to k. So we introduced a k during the lectures, and k is half of the size of the filter. So the middle one is 0, and it's minus 1 and 1, minus 1 and 1 um, on the left and on the right. So this filter just says you are multiplying the column number with the row number. So here, the column number is minus 1, the row number is minus 1 as well. So their product is 1. And similarly here, it's just minus 1 times 0 is 0, minus 1 times 1 is minus 1. And you can do it for this, do it the same way for the other ones. So that's our filter. And then when you convolve, you need to flip the filter. But it turns out that if you flip them, so basically going the other direction, 1, 0, minus 1, 0, 0, 0, minus 1, 0, 1, it turns out to be exactly the same thing. So flipping and not flipping is the same. And then what you do is just put this filter on top of this. So then you have mostly 0 except for this is a 1. So the first pixel you get 4. And similarly, if you put on top like this, then only you have a minus 1 here multiplying by 3. All the other things are multiplied by 0. So that's why you get minus 3 here. And then next, you just put it on top like this. And then minus 1 times 2, so it's minus 2. And the last one put on top like this. And it's 1 times 1, so it's 1 here. You can do the same thing for this multiplied by itself. So most of the terms are 0 if you just put the filter on top of, say, this part, then these are 0 and these are 1s, but they are multiplied by zeros. So the only one that's non-zero is when the filter is on top of each other. So here in the middle, we are calculating the convolution for this pixel, and it's 1 times 1 minus 1 times minus 1, and add them up, so you get a 4 in the middle, and every other pixel is 0. What's this? Okay, so here we are trying to find the hog feature descriptor. So we should draw these gradient. So 1, 1 is going that direction. 1 minus 1 is going that direction. 1, 1 is going that direction. 1 minus 1 is going that direction. 2, 2 is just a very long one going that direction. And minus 1, 1 going this. Minus 1, minus 1 that. Minus 1, 1 this. And minus 1, minus 1 that. So then we need to know the bins. So the bins are, these are being 1, and these are being 2, I think, because it's from 0 to pi over 2. So it's basically any direction like these, all the opposite directions, and similarly for the other bin. So we just need to add up the magnitude of the, the gradient facing this direction. Then you get the first bin number. Let's actually do this. So basically add this length, this one, and this one, and this one. So these four look like the same. They are all just 1 squared plus 1 squared square root, so square root 2 for all of the shorter ones. The longer one, you are actually asked to compute this. So it's 2 squared plus 2 squared square root, so it's 2 square root 8, so it's 2 square root 2. And so you have 4 of the shorter ones and 1 of the longer ones. So 4 times square root 2 plus 2 times square root 2. So this one is just that. These ones are this. And similarly for the other direction, you get this, and this. Add them up, you only have 4 of the square root 2 ones. So that's why the hog feature looks like this. The next one is the support vector machine with 1 versus 1 and 1 versus all. So for example, if you do 1 versus 1 for say if you have three classes, 1, 2, and 3. 1 versus 1 means I use these two to train one SVM like this, and you use these two data points to train another one, and then you use these two to train another one. So we call this 1 versus 1 SVM. So when you are training class 0 versus class 1, then you are only using these two sets of data points. So you are only using the sum of these two, so 30 data points. And if you do 1 versus all, then what it means is, suppose again you have three different classes. That it may be 1 point or many points in a cluster or something. But in any case, we just say this is class 1. I would label it 1 and label everything else 2 and 3 as 0. So that's what it means to have 1 versus all. So all means everything else. So I train a support vector machine like this. 1 versus everything else, 2 versus everything else, you get that, and 3 versus everything else, you get that. So in each case, you need all of the data points. You just label all the other data points as 0. So that's why you need all of them, which there are 100 data points in total. Next, what's the training accuracy on the split based on x2? So x2, if it's 0, if it's 1, if it's 0, then it's either 0 or 1, so it's not clear. So it may be 0, maybe 1, let's say half-half. And if it's 1, then all of the labels are 0, so I will label 0 here. So what it means is you have 4 data points. No matter whether you choose 0 or 1 as the label, you are always going to classify 1 out of 4 incorrect. And that accuracy is 75%. If you split according to x1, it actually turns out symmetric. So it's the same thing. You get the same number. So the interesting one is how to compute the entropy. So this entropy is just the probability of x1 is 1 times the entropy of y given x1 is 1. And probability of x1 is 0 times the entropy of y given x1 is 0. So probability of x1 is 1 is just counting how many there are. So there are 2 1s and 2 zeros, so it's half each. So it's half times the entropy of, given x1 is 1, there is half of it is 0, half of the x is 0, half of the y is 0, half of the y is 1. So this is basically the entropy of a random variable that's half 0 and half 1. And then you add half times the entropy of another random variable. This is both 0. So 100% 0, 0% 1. So the entropy for this is just half log to half minus half log to half. But you should remember that this is the maximum entropy binary variable, so this should be 1. You can check it. And this is a certain random variable, so the entropy must be 0, but you can write out the expression as well. So 0 log to 0 minus 1 log to 1, and this is 0, this is 0, so it's 0 as well. So basically you have half times this plus half times that, so you get half, and that's the answer. Next one is, you know the feature vector, so you just write out the feature vector. X1 would be 1, 1. So just substituting this number into this expression, and x2 is -1 squared, so it's -1, 1. So to find the kernel matrix, you just do phi transpose phi. So it's basically the dot product between these two. So basically, if you want to write them in notation x prime, then this is x prime dot x prime dot x prime 2, and x prime, these two are the same, symmetric. So it's like this. So this dot itself is 1, 1 dot 1, 1. So it's 1 times 1, 1 times 1. So it's 2. And this dot this is -1 plus 1. So it's 0. And similarly for the other two. So this. Next one is exactly the same, except for you have different features. So this is 1, 1, 1. And the other one is -1, 1, -1. So the first entry is this dot itself, so it's 1 times 1, 1 times 1, 1 times 1. Add them up, you get 3. And the second, this entry is x1 prime dot x2 prime, so it's this times this, -1 plus 1 -1, so it's -1, and similar for the other two entries. Okay, so the next one is Bayes rule. So the first part of the question is just asking the probability of observing an H. So you just like demarginalize this. So it's probability of H, it's just probability of HA plus probability of HB plus probability of HC. And HA, each one you can do it as using the conditional probabilities, probability of A, and similar for the other ones. So H given A, all of these are giving the question. So this is 0.1 times probability of A. Each document is chosen with equal probability, and there are 3 of them, so each one is 1 over 3. And this one similarly is 0.2 times 1 over 3. This one is 0.3 times 1 over 3. And you add them up, you get 0.2. And the next part is asking probability of the document is A given H. So just directly applying the formula HA divided by probability of H. You computed both of these before, so it should be very quick. AH is just this, so it's 0.1 times a third divided by 0.2 here. So you can just cancel all the 0 points, and then it's just 1 over 6. So it's this. Next one is just finding the MLE. MLE is basically a fancy way of saying just use counts to represent probabilities. So this is counting the number of A is 1, B plus C is 2, divided by counting B plus C is 2. So how many of these are 1? Some of these are 2, means both of them are 1. So only 1, 1, 1. So the count is equal to 2. And on the bottom is only counting B plus C is 2. Basically, there are only 2 choices, this one and this one. So the total count is 4 plus 2. So it's 2 over 6, 1 over 3. The next one is similar, it's just you have more things to add up. So it's counting A is 1, B is 1, C is 0, or B is 0 and C is 1. So how many are there? A is 1, B is, one of them is 1, so there are 2, 1 plus 1 in total, and you divide it by counting B plus C is 1. So how many of those are there? So these ones plus these ones. Right? So add the counts up is 0 plus 0 plus 1 plus 1. So that's why it's 2 over 2. So it's 100%. Next one is a common cause-based net. So A is here, and B and C are like this. So let's call B is 1 being B, C is 1 is C, and B is 0 is not B, and C is 0 is not C, to make the notations easier. So we want to find probability of BC. You need to basically, again, demarginalize A. So BCA plus BC not A. And in a base net, you can just take the product of their each one given their parents. So B would have parent A, and C has parent A, and A does not have parent, plus B given parent not A, C given parent not A, and not A. I think you know all of them. B given A is this, 0.2. C given A is 0.3. A is 0.1. B given not A is this, so 0.4. C given not A is 0.5. And not A is 1 minus A is 0.9. So take their product, add them up, so you get this expression here. And the next thing is C given B. So this is just BC divided by B. And let's do the same thing for B. So B is just BA plus B not A. Because of this common cost structure, B and C are given A, B and C are independent. So I can add all combinations of C, but it's not necessary. So because if I add C, A and C, then they will be independent. So the sum will be the same. So here BA is just B given A times A, so it's 0.2 times 0.1 plus B given not A, that's 0.4 times not A is 0.9. So that's how you get probability of B, and you just put it on the bottom and you put the answer from the previous question on top. So it's exactly the same for C, so I'll not repeat this. The next one is you start with the character A, and then you want to find the simulated using CDF inversion, how to simulate the next two characters. So first, after A, the probability distribution is A was probably 0.1, B was probably 0.2, and C was probably 0.7. So the first thing is to find the CDF of that. So CDF, you are just adding up the consecutive ones. So if it's between 0 and 0.1, then the random character will be A. And if it's between 0.1 and 0.3, again, it's just adding up consecutive ones. And then the output is B, and it's 0.7 plus 0.3, so it's 1. So if it's between 0.3 and 1, then you output C. So here, U1, the first random variable is 0.5, so it's in between 0.3 and 1, so the output is C. And let's do the same thing for the next one. Next one, we are starting with C. So the distribution we're looking at is this row here. And then we compute the CDF again. So the CDF starting with 0 and add the next one. And then this add the next one, 0.7. 0.7 add the next one is 1. So between these means A, between these means B, between these means C. And again, it's another 0.5. It's between 0.3 and 0.7. So the next one is a B. What about the question here? It's just asking for the probability the next two is B and C. So given starting from A, the next one is B with probability 0.2. And now the first letter is B. So starting from B, the next one is C is 0.5. So you just multiply them together, you get the answer. Okay, so the last one, you are given the information gain calculations, so you just want to find the maximum spanning tree. So let's say A, B, C, D like this. A and B 0.1, A and C is 0.2, A and D is 0.3, B and C is 0.4, B and D is 0.5, C and D is 0.6. So you can start with any node or any vertex, and then you will get the same tree. So for example, if you start with A, then just find the, the edge with the largest information gain from the tree I already have, which is only A, to something else. So here's 0.3 is the largest. So I will add this edge and add this vertex to my tree. So now my tree is AD. And then starting from my tree and to anything else, so there are many choices, 0.1, 0.2, 0.5, 0.6. 0.6 is the largest, so I'm going to add this edge and add this vertex to my tree. So now my tree contains 3 vertices, and then you do the same thing, right? So you have from the tree to something not in the tree is either this or this or this. Largest one is this. So I'm going to add B at the end. So you will always end until we add everything into my tree. So now my tree, you still need to pick a root. So suppose you pick the root A, then your tree is A going to D and D, B, C. So the edges that are included is AD, BD, and CD. All the other edges are not included.